In this work, we present an online inertia identification method using convex geometric regularization for physical feasibility. Reliable knowledge of the inertia information is essential for efficient planning and precise control of autonomous physical systems. This fundamental problem is challenging due to the intrinsic nature of parameter space as well as the external factors. The usual least squares with L2 regularization fails to achieve physically consistent estimation. Many different methods have been developed to address this issue, but still there is a gap in physically consistent online identification. This study aims to develop a recursive algorithm that combines the benefits of online learning and geometric convex regularization. We developed a new method by extending the prior work where the same objective function is considered for batch optimization. The inertial parameters of rigidity consist of mass, components of the first mass moment vector, and components of the rotational inertia matrix. Previous works have identified a set of inequality conditions that altogether describe the physical feasibility of these parameters. Interestingly, the positive definiteness of the 4x4 pseudo-inertia matrix compactly represents all requirements, and this condition describes the geometry of the space of inertial parameters. For our purpose, here we consider a mechanical system dynamics that can be presented in generalized coordinates. By collecting the inertial parameters and some unknown extra force modal parameters like friction coefficients into a single vector theta, the multibody system dynamics can be rearranged into a linear parametric form which is suitable for regression tasks. Let us formulate the problem to be solved at each time step k. First, we suppose that the optimal solution for the previous time step is available. Second, we represent the parameter for step k with the update delta k from the previous estimate. Then, our problem is to find this delta k that minimizes the weighted sum of fitting objective, an optional forgetting objective, and a twice differentiable convex regularizer. We choose the Bregman Log-Determinant divergence for the pseudo-inertia matrices as the regularizer, since it acts like a barrier function that keeps the pseudo-inertia matrix within the positive definite cone. Clearly, the objective function jk is a smooth and convex function, so we need to find the parameter update delta k so that the gradient of jk vanishes at theta hat k. Using the fact that the previous estimate is optimal with respect to the objective function for step k-1, we can simplify the equation that should be solved for delta k. Here we notice that the regularizer has closed form expressions for the gradient and the Hessian, so we can easily expect that the Newton-Raphson method will readily solve the equation. For implementation, we first initialize the parameter with a prior value. Then, at each step, we update the information matrix, then apply Newton-Raphson method to find the right increment, update the parameter, and repeat the same process. The weighting factors in the objective function are the design parameters of the proposed method. Many different strategies can be adopted to adjust the weighting factors over time, and the examples are adaptive regularization strength and the directional forgetting. We performed a numerical experiment using the publicly available dataset for the MIT Cheetah 3 leg assembly. 3 different methods are compared to show the effect of different choices for the regularizer and to compare the result between online and offline identification. Constant weighting factors are considered for this experiment, and the regularization strength is chosen to achieve the same level of RMS value for the Hawk prediction error for fair comparison. Here we visualize the evolution of estimated mass distribution over time with ellipsoids for each method. The animation clearly shows that the proposed method on the right-hand side, with geometric regularization, provides much more consistent estimates that match well with the bodies, whereas L2 regularization, shown on the left-hand side, provides irregular and inconsistent results due to physical infeasibility. The results show that, regardless of the sampling rate, the proposed method yields physically feasible estimates for the inertial parameters and recovers the same result as the batch optimization. Notably, the estimated mesh matrix is also always positive definite with the proposed algorithm, which is an essential requirement for many robot control schemes for stability. At each step, the parameter update could be computed within at most 2 Newton-Raphson iterations. The time histories for the parameter estimation error and the predicted joint torques show that the proposed online method recovers the offline identification result. Now, look at the red circle, which shows the RMS value of the torque prediction error with the current estimate for the unseen future state. The result indicates better generalization performance of the proposed method, especially in the low data regime. In summary, we developed a recursive least squares method that provides physically feasible estimates for the inertial parameters and positive definite estimates for the mesh matrix. The recursive method is memory efficient in the sense that we don't need to store every input-output pair, data efficient in the sense that we achieve better generalization performance in the low data regime, and compute efficient in the sense that the update can be found in no more than 2 Newton-Raphson iterations. Thank you.